Now, are we done, or are there more things that we can do? Well, I think there are a couple more. We can put mass together with either initial or final velocity to get kinetic energy, the initial kinetic energy, the final kinetic energy. So I'm going to kind of do a loop around here. I'm going to go V naught down to here, and I'm going to connect the mass here. And I'm going to say from mass and V naught we can get the initial kinetic energy. So what's the relationship there? Well, I am out of colors, I think. But we have initial kinetic energy equals 1/2 m times the initial velocity squared. And with the final velocity and the mass, we can get the final kinetic energy. So final velocity, bring it all the way around here, and put mass here, we can get final kinetic energy. And the final kinetic energy is 1/2 m times Vf squared. Okay, now that we have initial and final kinetic energies, is there anything else that we could connect? Well, yeah, and looking at it, I realize that I've left off some important subscripts, so I'll kind of give it away, but hopefully you've seen it. This is delta W net, is net force times delta S, and this is, of course, delta W net, work done by the net force, by the total of all forces. And the work done by the net force on an interval is equal to the change in the kinetic energy on the interval. So from the initial and final kinetic energy, we can get, got the wrong color here, we can get the change in kinetic energy and we have the triangle there. I haven't completed this triangle. I would have to complete, I'd have to connect mass with initial velocity to complete this big, almost heart-shaped triangle, and mass with final velocity to complete this. I could do that, but it would get kind of messy. So I'm going to kind of leave the third side of that triangle off, but it should be clear what the third side is. And that, if we know any two of the three, initial kinetic energy, mass, initial velocity, this relationship allows us to find the third, because there are only three quantities related by this equation. Similarly with final kinetic energy, mass, and final velocity. Okay, well, do you see other relationships that we could make from this diagram? Now, I'm going to leave it at this. You can see if you can think of anything else. One thing I note that we really cannot do is we can't pair the mass with the change in velocity to get the change in kinetic energy. Now, if we know the mass and the change in velocity, we just can't determine the change in kinetic energy. You can think maybe about why. If we know the mass and the average velocity, we can do the 1/2 m times the average velocity squared, but that is pretty much a meaningless quantity because it does not give us the average kinetic energy. Reason being that the kinetic energy is proportional to the square of the velocity, so the average velocity is a linear average of the initial and final velocity, and it doesn't articulate with the idea of kinetic energy. I don't want to say any more about that right now. You have to be fairly adept with algebra to understand what we mean by that. But take my word for it, it just isn't so. And there's similar reasons for the mass, and the change in velocity doesn't give you the change in kinetic energy. If you did 1/2 mass times change in velocity, you would not get change in kinetic energy. Okay, the only other thing that I'm going to say here is that the kinetic energy and the work done by the net force are, of course, equal. So that, since these are equal, you could complete a triangle between initial kinetic energy, final kinetic energy, and work done by the net force. Now don't pay a lot of attention to the things I've added here, but I had delta W equals F net delta S should be delta W net, and this should be delta W net, because obviously this is the work done by the net force, and we want to, the work done by the net force is the net force times delta S. We'll talk about the rest of this in a subsequent video, so don't pay any attention to it now. You kind of ruined the experience.